Okay. I don't know why. Because I missed out. You were great. Yeah. I was like, damn.
Good morning, everybody. Thank you for joining us for today's workshop. Dr. Yaser Baseri and I are going to present to you the beauty of quantum computing and the risk as well. So we all take care and to be prepared for the risk. So we will present this presentation together. So I'll start. So in today's workshop, we will go through introduction to the quantum computing. Why quantum, what's the qubit, entanglement, and all these beautiful features that quantum mechanics brought for us. And then we will move to the migration strategy because of the threat that quantum computing brings. We need to migrate to new solutions. We will go with you through a migration strategy, an effective one that we all should follow to tackle such problem. Then we will conclude our talk by giving you a list of recommendations and final remarks. To start with, as we all know, we started with big, giant computers in the 60s, 80s, 70s, and like really huge computers that they do simple calculations. And by the time we end up having smart devices, smartwatch, everything is small and smart. But the sad truth is we reached our limit. We cannot make these devices any faster. And as you can see in Moore's law here, we already reached a plateau. We cannot make these devices any faster. Why? As you can see in this figure, we have Intel CPU. And in this, like Intel has backed about 100 million transistors in each square millimeter. So we cannot make them any smaller. And if we do that, we cannot control the heat, we cannot control the noise. So the current technology reached the end. We cannot make it any faster. So what can we do for this? What we do is, and what we think is, quantum computing is the solution. Why it's the solution? Because it brings new way of thinking. It's not the traditional thinking that we have, but new ways of solving the problem. Well, why is that? If we compare the classical computing that we have, it is similar to comparing the classical world and the quantum world that we have as well. So in the classical world that we have, we can simulate it as a car, a big object that you can do whatever you like about this thing. You can measure the position and the momentum of the car at the same time while it's still moving easily. We can do that. However, in the quantum mechanics or the quantum world, we are dealing with tiny, small, massless objects that you cannot do so many things with them easily. And if you do, you disturb them. So, like, for example, the electron that orbits the nucleus, so you cannot measure the position and the momentum at the same time. You can only choose to measure the position or the momentum. And if you measure one of them, you disturb the other. So this weird phenomenon of these tiny objects give us a new way of thinking of doing processing. So in the classical computing, what we all have now is we have what's called bit, classical bit. And bit is the smallest storage unit that we have to store on it either 0 or 1. We store either 0 or 1. In the quantum computing, we have what's called quantum bit, for short, qubit. And still, we can store 0 and we can still store 1. And the beauty about it, the new thing that brings to us is we can store them both. We can store 0 and 1 at the same time. And we can deal with this object as if it's 0 and 1 at the same time. We can deal with it as if it's both. I'll go with you through a demo just to show you how it works. Here. So, in here I'm using IBM simulator. It is online and it's free for everybody can use it. Just to show you the idea of qubit and how it works. As you can see here, this is a representation of the qubit as a 3D object. And as you can see here, we have a single qubit, which is here, qubit 0. We have one qubit, and it is in the state 0. It's not initialized with anything. It's just empty. So the initial state, which is 0. We can have it in the state 1 by flipping this qubit. And as you can see here, the qubit state or value was 0, but now it moves to 1. And as you can see here in the 3D representation, it moves from up to down, which is the 1. So this is classic. Yeah, it's still here. It is classic. We have 0, we have 1. But where is the superposition, which is the weird phenomenon of quantum mechanics? So here, what we need to do is to replace the gate. We add the Hadamard gate. And as you can see here, the beauty of Hadamard gates, the qubit now, it's 0 and it's 1 at the same time. And if you measure it, there is a 50% chance of finding it 0, a 50% chance of finding it 1. Nobody can tell what's in it unless you measure it. So the measurement is the barrier between the quantum world and the classical world. After you measure it, you find the classical input that this qubit has. So, but in doing processing, you can do processing while it's in this state, and if it looks like you are doing processing with both the states at the same time. So, if I can go back. So, how can we do this? How do they do that actually? So we know for the classic we have electric pulse. If there is an electricity there or no, if there is a voltage or not. But here, how do they do that? There are so many technologies to do that, and one of them, and the simplest that I can explain here, is the use of electrons. They use photons, they use electrons, they use so many things. But here we can represent it in this way. So we have this electron that's orbiting the nucleus, and there are two levels. The first one is called the ground state, the outer one, the excited state. So we can encode the information in this way. If we find the electron in the first level, the ground state, we call it the state 0. Now it's 0. So how to move it to the state 1? We just give the electron a little bit of energy. We give it a beam of light that will give it a little bit of energy. By doing so, I might use the laser better. So the electron is in the first level, the ground level, and if we give it a little bit of energy, it will be excited, moves to the second level, which is the excited level. So now we have the classic here, 0 and 1. And if it's 1, we can take energy from the electron and it will move back to the ground state. But yeah, this is classic. Where is the superposition in here? How they do this? The superposition, it's in this way. We don't give the electron enough energy to migrate to the next level. We just give it half of the energy. So whatever the energy that's required, we just give it half of the energy. What would happen now is the electron will be either in the first state or in the second state, but we will never know unless we measure. We cannot know. It's everywhere. And just to let you know, the word quantum comes from this thing. It is quantization. So the electron will not stay in the middle. The electron either in the first or in the second. It will never stay in the middle because it's quantized levels. So now the electron, it's in the superposition, and we don't know whether it's 0 or 1 unless we measure. So this is just one of the representation of qubits to give you the idea. So we have different gates, quantum gates, to manipulate this qubit. And as you can see in this 3D visualization, all what we do is just we are rotating the qubits around an axis. We have X, Y, Z axis, and you keep rotating it. And this gives the qubits the beauty of being reversible. Whatever you do to the qubit, you can reverse it back. And most of the quantum gates are reversible as well. Yes, the superposition is beautiful. It's amazing. It gives us so many advantages. But the entanglement is the most important thing in quantum computing and in the quantum mechanics as well. Why? Because it allows us to link two qubits to each other. So yes, we have one qubit that's mystery, but what if we connected two mystery qubits? Now we can connect them in two different ways. Either we connect them to be equal, to be always the same. What does this mean? It means like here the state they are equal, here the state they are opposite to each other. If they are equal, it means like if you measure one of them, the second one should have the same value. So if you find the first one 0, the second one should be 0 as well. If you find it 1, the second one should be 1 as well. And we can entangle them to be opposite. If the first one is 0, the second one should be 1. I'll go with you through a demo just to show you the entanglement, how we create it. But before the entanglement, let me add another qubit. Here we have 2 qubits. And just to show you, so these are 2 qubits because they are empty. They are in the state what? 0, 0. Both of them 0, 0. If I flip one of them, now one of them is still 0. The other one, because we flipped it, it's 0, 1. Now the 2 qubits are in the state 0, 1. One of them is still 0. The other one we flipped it. So we can manipulate all of them in the same way. So we can flip them both. Now they are both 1, 1, not 1, 0. So, and let's now make them, get them the superposition state. So if we add Hadamard to both of them, this is visualization, it's IBM tool, which is amazing. So now what's happening in here? We have 2 qubits, both of them in the superposition. What does this mean? Both of them, they don't know what they are. They know, but we don't. So with either 0 or 1, the second one either 0 or 1. So we have all these possibilities. If we go to measure them, we might find them 0, 0. We might find it 0, 1, or 1, 0, or 1, 1. Equally, the same amount of probability of occurrence, they have it all. Either 0, 0, 0, 1, 1, 0, 1, 1. But what if they are entangled? Here is the beauty of entanglement. So now they are entangled. If you go to measure them, you will either find them both 0, 0 or both 1, 1. You will never find them 0, 1 or 1, 0. I mean, theoretically, if there is an error, you can find them 0, 1 or 1, 0. But theoretically, they should be in this state either 0, 0 or 1, 1 because they are entangled. We can flip one of them and we will make them entangled opposite to each other. So if you find the first one 0, the second one should be 1. If you find this 1, the other one should be 0. So this is the beauty of entanglement. We have so many libraries to do quantum programming, and one of them, the one that I was using here, which is Qiskit, I can do the same circuit for you using Qubit as well. So you define how many qubits you want, how many classical registers you want, and you design the circuit. Here is the circuit. I did Hadamard and control knot, the same thing. This is Hadamard, this is the control knot. I will remove this. This is the same circuit, Hadamard, control knot. You can just do it here. Then you measure the qubits. This is the circuit that we designed here. And this is, you do the simulation, and this is the states that you can find. So you can run these experiments locally in your machine using the simulator, or online simulator, or in actual quantum machine. Because IBM offers a 5-qubit quantum machine for free, you can access it and do your experiments. So all these programming languages are great, and most of them are in Python, and everybody can go easy. So these advantages gives us what's called quantum supremacy, which means we can do processing faster than the classical world. Why? If I have a machine that has 8 qubits, it's equivalent to a classical machine that has 256 bits. So the same amount of processing. So I can do it in 8. I need to do it in this amount of classical bits to do the same computation power. Why? Because of the superposition. Because I can store them both, while here only one of them could be there. I cannot do processing in 0 and 1 at the same time classically, but in quantum we can. We have different types of quantum computers, and we have a very specific quantum machines that they only do specific problems. They only solve specific optimization problems, and we have the beautiful and the most important one, which is the universal quantum machines. These machines, they are similar to what we have, general purpose. We can use them for solving any other problem, and this is the dream that everybody in the world is looking for. So not only us, all of these companies are interested in quantum computing, and they are all building their quantum machines, and they are trying which one of them will do this faster than the others. And They are trying, like especially the giant companies, they are building a universal quantum machine, and the small companies, they are trying to build smaller devices, systems, softwares, and things like that, algorithms. So what all of them are trying to do is to optimize this problem. What's the problem? We need bigger quantum computer, but we need less errors. Because now what we are suffering from is the errors. If we minimize the errors with bigger machine, the problem solved. And this is why they think the technology is not ready, because of the errors. But maybe within 5 to 10 years, this technology will be mature enough and will be ready. Yes, we have this beautiful machines that we can use them to solve our critical problem, but they bring problems as well, especially for us in the cybersecurity field, which is the quantum threat. What's happening in here is all our information in the internet is in danger. Why? Because we all use the internet to send and receive information, and all these information use protocols. These protocols rely on what's called public key cryptography systems or asymmetric encrypted systems like RSA. And why these algorithms are beautiful? Because they have two keys. One, you encrypt using one, I decrypt using the other. So there is no problem of key distribution. I can use another algorithm, but I need to give you the key. How to give you the key? It's an issue. But public key cryptography solves this issue, and all the protocols in the internet relies on these protocols. And the sad story is they are not secure anymore. They are in danger. Why? Because of this guy, Shor. Shor is the first one to introduce quantum algorithm, and its first quantum algorithm is called Shor algorithm. This algorithm breaks RSA algorithm and all factorization problems that rely on factorization problem algorithms. And the circuit that he designed or crafted, it can factorize a number in seconds if we have a big machine. In seconds. Compared to the classic, we need billions of years to do that, but in seconds using classical computer. How he does that or did that, just take this as a simple example. We have a number which is 91, and this number, its factors are 13 and 7. So how can you find this 13 and 7? Because if we multiply, we get 91. How can you find this? The trivial solution is try and error. You try two numbers, try. How many numbers you can try if the key is so long, like 2,000 bit? So you need billions of years until you finish all these tries. So there are other smart solutions. One of them is called period finding. Instead of finding a number, you try to convert the problem into a wave function, which is this thing. How you do that? You take a random initial number. Here I have 4, and here we have 19. And we raise it to the power of x, and we take mode, the number that we are trying to factorize. By doing so, you will generate a wave function. As you can see, it repeats itself. This way, it repeats itself. And with another initial, it repeats itself from here to here, and this is similar here. So there should be a period. After time, these numbers repeat themselves. Once you find this period, you feed it to another algorithm, simple algorithm, classical one, GSD, and it will give you the numbers. Doing this classically is terrible. It's harder maybe than the random search, but in the quantum, in a blink of seconds, you can do that. Because of the superposition, you work on all of the possibilities at once. So this is what's expected. Having a quantum computer can break these algorithms in a linear time, while the classical time required for breaking these algorithms is increased exponentially. And as you can see here, for RSA 2048, you need billions of years to break this algorithm. The other beautiful algorithm for quantum computing is it's called Grover's algorithm, and it's for unstructured search. You have data that you need to search on it, but it's not structured. So this is the data that you are searching on it. So we have n record. Let's say you are searching for this X. The best algorithm that we have is to check them all. There is no other solution. There is no way to find it unless you check them one by one, until you find it. Why? Because it's not structured. So, however, Grover, he crafted a quantum algorithm that it will save us a lot of time in doing so. So this is the classical one. In the classic, you need at any time, so the time increases linearly by the data. However, in the quantum algorithm, the time requires it's only a square root of it, which is a really great advantage. So this is the algorithm. I will not dig deep on this. And next, this is a quantum risk. Yes, we have this thing, we have this thread, how to do the risk, and my colleague Dr. Yaser Baseri will present you.
Thank you, Mohammed, for a great presentation. And I will continue with this presentation for quantum risk. So, yeah. So we have quantum computer with a lot of capabilities. We have Shor and Cobalt algorithm. They can weaken our security system. So we need to evaluate the risk associated with this kind of threat imposed by quantum computer. Let's take a look at NIST crypto standards. There are a bunch of standards related to cryptography presented by NIST, National Institute for Standardization. We can categorize them into public key-based standards, symmetric key-based standard tools, and guidelines. This chart summarizes some of particular standards we have in NIST. Quantum computer would impact what it is in red box, the public key cryptography. The public key cryptography we use today is based on either factorization or discrete logarithm problem. And it could be vulnerable to quantum computer and quantum attacker who access to quantum computer. And this is standard, and the standard we have here should be replaced with new algorithms. So FIPS 186 and NIST 856 APC are not usable anymore. What about symmetric key? For symmetric key, the impact is not as dramatic as public key. Quantum computer can impact standards, for example, for symmetric key like AES, SHA-2 and SHA-3. But with using linear key, still we would be able to use the same standards, and they are still usable. So here is a list of some common classic algorithms today. We have here elliptic curve cryptography, we have finite field Diffie-Hellman, we have RSA, AES, SHA-2 and SHA-3. The first three ones are related to public cryptography, and the last ones are related to symmetric one. As you see here, it often takes 10 to 15 years work through invention, the standardization, all the way to widely used. Often take many years to discover the attacks on each of these algorithms. And knowing what we know today is that large-scale quantum computer will break the asymmetric algorithms which are used today, like elliptic curve cryptography, finite field Diffie-Hellman, and RSA. So the first three ones are not usable anymore. Because of invention of quantum computer and using Shor algorithm to break those schemes. And the last three ones can be weakened by Grover algorithm, but still are used. They are still usable. As it's shown in the previous slide, the standardization and replacement of algorithms are a line process. It often takes 10 to 15 years, which should be done right now. It takes many years to go through design, analysis, implementation, testing, and deployment of new cryptographic algorithms. So we need time to get it right, build agility, and potentially modify the system architecture. For this process, there are some recommendations and best practices. One of them is quantum readiness best practices of Canadian National Quantum Readiness Best Practices and Guideline. As you see in the page 9 of section 4 of this recommendation, there's a chart showing that it takes maybe 10 years to planning, scoping, and implementation of the process. So this process is a line process which should be done right away. So we should migrate to new technology of post-quantum. So we should have a plan for that. Migration plan can be consist of 8 levels as shown in the following. It includes exploitation, standardization, protocol, implementation, community, research, and agility. Now, we have, for this chart, we have 7 steps. So, at the end of each step, we have some changes. So, each changes can cause some kind of risk and threat to our system. So, where can we do risk assessment for this migration? Should we do it in the starting point? Should be done at the end point or for the whole process? Since in each step we have some changes, risk assessment and preparation should be done during the whole process. And to evaluate the risk and threat caused by any changes to the systems. Now, the next question is that why we need quantum computers and why we need to assess the risk of quantum computer. Nowadays we have weaponized cyber tech. They have different types of attacks. They can run ransomware attacks, breaches of personal information, or hacking to grab IP. But what if they have access to quantum computer? With the help of quantum computer, the adversary can have more power to break cryptographic protocol and resulting in new attack. The adversary can help. The adversary can help with the help of new computer can decrypt what we have now. So the adversary can store all the information encrypted by classic computers and classic solution now, and with the new capabilities of quantum computer, the adversary will be able to decrypt this encrypted data. So it's a kind of store and harvest. It's stored today and decrypt later. So we should be worried about the data that is available today to be used in future. So For risk assessment, what should we do? And what's our migration strategy? The first thing that we should do is we should identify the organization's reliance on cryptography, where the cryptography is used, what type of cryptography is used, and how long does this information need to be secure? How long does the information need to be secured for? We should also track the development of quantum technology and progress of quantum computer and providing fault tolerant, more fault tolerant qubits. We should also manage technology's life cycle to adopt quantum resistant technology. So, NIST cybersecurity framework, which was proposed for risk associated to any kind of cybersecurity, as a quantum or classic or any other type, includes 5 steps: identification, protection, detection, response, and recovery. In identification, one of the aspects is risk assessment. As you see in the bottom part, risk assessment process phases, according to NIST, includes 5 phases, which include threat source and event vulnerabilities, likelihood of occurrence, magnitude of impact, and determine risk. By evaluating the likelihood and impact of any vulnerability, we would be able to assess the risk associated to them. The risk associated to this vulnerability can be evaluated as quantitative by quantitative risk assessment or qualitative risk assessment. In quantitative risk assessment, we need to have comprehensive knowledge about the system and technology we have. Since for quantum computer, nowadays we only have abstract view. We only able to assess the risk based on qualitative risk assessment, which we need less information and less time to evaluate. For qualitative risk assessment, we consider 3 levels of likelihood, including grad, moderate, and high. And impact are classified into 3 levels: low, medium, high. And since risk evaluated by the multiplication of likelihood and impact, by this chart we will be able to assess the risk into 3 levels: moderate, low, medium, and high. So, to assess the risk, we need to assess likelihood and impact. We need to have some established criteria for likelihood level and impact level. Here are some examples presented in this reference for likelihood and impact. The criteria for impact. As an example, the threat that might cause loss of human loss can be considered as high threat, high impact level for threat, and the threat that might cause disclosure of non-critical information considered as low level for impact. So cybersecurity can be categorized and assessed for their risk using the strike threat model. A strike threat model is a categorical risk assessment model originally designed by Microsoft and invented by Microsoft for software to detect any kind of threat related to spoofing, tampering, repudiation, integrity, denial of service, and elevation of privilege. For quantum risk assessment, we can use the same model to analyze cyber threat. Now, we need to analyze the risk associated to quantum machine. We should consider a methodology. Global Risk Institute suggested a methodology including 6 phases, which are described in the following. The first phase is identifying and documenting assets, their current cryptographic protection. The second phase includes research the state of emerging quantum technology and the timeline for availability of quantum computers. Now, at this point, we should have scheduling and evaluate time to migrate. For evaluating time to migrate, we need to consider three factors. The amount of time that an organization will have to migrate the system to post-quantum 1 depends on 3 factors, as I already mentioned. Migration time, which is the number of years the organization needs to migrate all of the system that handle its important data to new quantum-safe cryptography. Shelf lifetime, which is the number of years that organizations' important high-value information need to be protected, and the threat time is the number of years before relevant threat actor will be able to break the organization's existing quantum vulnerable cryptography. For the last one, NIST predict in 2015 that with 1/7 chance of breaking RSA to 2048 by 2026, and with half chance by 2031. Here is a summary, comprehensive summary of the likelihood of predicted likelihood of breaking RSA in 5 to 30 years. If the migration time plus shelf lifetime more than threat time, then we should be worried because the attacker can break the systems. So, as I mentioned earlier, methodology include 6 phases. The first 2 phases has been mentioned already. The next 2 phases are including the identify and document threat actors and estimate their time to access the quantum technology, and identify the time required to migrate the organizational technical infrastructure to quantum safe and lifetime of your asset. And the last one is determining if X plus Y more than Z. In the last phase, phase 6, we should identify and prioritize the activities required to maintain awareness and to migrate the organization's technology to quantum safe state. We have 3 inflection points in this process. NIST standardization point is the first one, and we should be ready 75% by the time of planning, testing, and deployment. The second inflection point is related to fault-tolerant logical qubit. Logical qubit is a starting gone to scaling these devices, which made the threat more clear. There's a serious likelihood that in a relatively small number of years to the point to be cryptographically relevant, and we should be 90% ready by that time. The last inflection point is commercial line is related to commercial line distance quantum key distribution, which introduced quantum key distribution networking into existing network and key management environment. In the next session, Mohammed will describe this and the third inflection point in more detail. So there's a risk. There are some risks associated to this migration. What's the possible solution? The first one is quantum cryptography, which is an additional tool to our crypto system, which gives an extra layer of defense in depth. The second one is large-scale quantum communication network and quantum internet. The last one is post-quantum cryptography or post-quantum resistant algorithm. In the following, we describe each of them one by one. I asked Mohammed to come and continue discussion about quantum cryptography and quantum networks.
Thank you, Yaser. I will start by reminding you about the two beautiful features of quantum mechanics, quantum computing, which is the superposition and entanglement. These two features gives us the ability to do faster processing because we deal with two quantities at the same time, and it gives us here the ability to link qubits to each other. Not only two, we can link as much as possible as we can to each other. So if you manage to manipulate one, you manipulate the others without even touching them or anything to them. So these two great features, along with the other one, which is the most important feature in quantum networks, it's called no cloning. In the classical world, what we currently have is if I send you a message, anyone in the middle can intercept this message, make a copy of it, then we'll send it to you. I can't notice that, you will never discover that, and we will never know that. And this is what routers are doing. We all connect to routers. What the routers are doing, they receive the packet, they do processing to it, they can copy it, they can do whatever they want, and they will forward it. Can they do this with quantum information? The answer is no. So you can never have a cloning machine that will receive a quantum state and gives you two copies of it. This is not possible for quantum, especially if the state is an arbitrary state that you don't know it. If you know it's zero state, you will create new one. But if the state that you don't even know what the state, there is no machine at all that can do that, not even theoretically. So this feature is amazing. Just imagine if you send me an information and nobody can copy it in the middle. This is a really great feature of quantum mechanics. The second one, which is great phenomena, which is the wave particle duality. The particles, when you send them, like the photons, when we send the photons, they behave in a weird way. What this thing is? These photons behaves in two different ways. They behave as a wave and they behave as a particle at the same time. So these particles, when you send them through this double slit wall, once they enter these slits, they will not just only lie on this space and this point. I use the pointer. So they will not. So this is what we think about it. What we think is, if the photon enters from this, it will land here. And if it enters from here, it will land here. But this is not what's happening. What's happening is this. We find particles everywhere here. This implies that the photons behave as a wave function, not as a particle. But if we try to monitor them, if we add a monitor here, a device that monitor these particles, where are they going? We need to know how this particle moved from here and landed here. We need to know that. We couldn't. we can't, and until now nobody can tell us. Why? Because once you add a monitor here, they start to behave like a particle. They change their behavior. Like if they know there is someone who is monitoring them. So just imagine if we are sending our information in this way. So the particles themselves, if there is anyone who is monitoring them or trying to measure their state or to know their existence, they will just collapse. They will not behave as a wave. They will start to behave as a particle. So which will give us a great advantage in using them as quantum networks. So yes, we have superposition, entanglement, no cloning, and also this feature. So this will allow us to create networks. This is just two examples of classical network that we have. Either two machines, they can talk to each other directly, and we can do this in quantum world by having simple, small devices. Prepare a photon, send a photon, receive a photon. We can do this using fiber optic. We already have the technology. We don't need big quantum computer here. Here, it's already in practice. Just small devices. But we have a problem here. Let's say the distance is so long. We need a repeater in the middle, right? This signal, it might decay. So we need a device that can take this signal and repeat it to the other end. So if we go back to the no cloning theorem, a repeater is not allowed to copy this state. How can we solve this problem? So quantum mechanics will never stop blowing our minds away. This is what's called quantum teleportation. So the quantum teleportation, you will have in the middle, the repeater is a teleporter. So if you receive the qubit, it will just teleport it to the other end. It will just, there is a mathematical manipulation here, or device that can do this. It will teleport the received qubit to the other receiver, but without measuring it. So if this teleporter try to measure it, the state will die. Try to copy it, he cannot. If I send him one, he can teleport only one. He cannot teleport two, one for himself and one for the others, which is great advantage of quantum mechanics that allow us to secure our information in transit. So what we are dreaming of is having quantum internet. Just imagine all these routers, everything is quantum based. All the information, they secure themselves. They don't need any other measures to secure them. They are secure by nature. So there are several applications that we can do that. And I will just go with you through the simplest example of quantum networks or quantum internet, which is the quantum key distribution. Why we need the quantum key distribution? Why we are here from the first place? Because of RSA. What RSA brings to us is, it allows us, it solves the problem of key distribution. I don't need to send you the key. I can give you the key publicly. Everybody knows the key. You encrypt using that key, and I decrypt using my private key. So the problem is solved. But these algorithms are broken, so we can use quantum machine to give us this key. Then we use symmetric algorithms because they are still secure. So we can use devices to give us this key. How? I'll go with you through the simplest example that I can come up with to give you the idea of this technology. We all use sunglasses. Why we use them? Because the sunglasses allows some of the light to pass and blocks the other. As you can see in this, like this sunglasses blocks the red light, which is polarized. So the idea in here, we have the light polarized. The light that comes from the sun is unpolarized. What does it mean? It means it oscillates in all the directions. Here, the light oscillates in every direction. We can have light that only oscillates up and down, which is vertical. So the photons themselves, they only move this way, like vertically. Or you can have them like polarized horizontally. They move in this way. And this is what this sunglasses blocks. It blocks any light that comes in this way. So this light, it comes reflected from the surfaces, from a water on the street or something like this. So this eyeglasses or sunglasses can block it. So let's take this scenario. We have light that's polarized vertical. So all these scenarios, the light is vertical. So the light moves in this way. And we have filter in front of this light. This filter as well, we can have it in a way like the holes or the slits on it, either horizontal or vertical as well. So in this first scenario, as you can see here, so this is the filter which is vertical, and the light is as well what? Vertical. So all the light will move through because the filter will not block it because they are aligned. However, in the last situation here, the light is vertical, the filter is horizontal. All the light will be blocked, nothing left. So no light gets through. So what happens here, because the filter and the light are orthogonal to each other. So we can have another situation where the filter is diagonal. Here is the beauty here. The diagonal here, this filter will deal with the light as it's in the superposition. What does this mean? Half of the light will pass, 50% will pass as if it is what? As if it is vertical. Half of the light will behave as if it's vertical. Half of it will be blocked as if it was horizontal. So now you can just imagine, just by changing the angle of the filter, we manipulate the information. So this simple example, it's quantum. Yes, the eyeglass that you deal with it's quantized by nature, and it's used in the very first big protocol proposed in quantum key distribution. What's used? The same concept. We have a source of light. The sender chooses the filter. I choose the filter. I choose it to be crossed, which is this one. So I will input my information to be crossed. Horizontal 0, diagonal, it means 1. Or I can use it, which is diagonal here. If it is to the right, like diagonal right or left, 0 and 1, and so on. So what we can do here, the receiver can choose the filter, the sender. So the sender chooses the filter. The receiver also chooses the filter. So if I send you 0 in diagonal filter and you receive it using diagonal, you should receive it 0. But if I sent it 0 and you receive it using diagonal, there is probability. Maybe you receive it 0, which is here. Maybe you will receive it 0, or maybe you will receive it 1 because you are diagonal to my axis. So this is the very first protocol. I will not dig deep here unless there is someone who needs a question here. So by just changing the filter, we secure the communication, and we can detect if anybody in the middle try to steal this information. So if you have here another filter, the information will reach the other end. Not all of them will reach, and they will be corrupted as well. So yeah, this is the very beginning protocol. And this technology, I will not dig deep, but there are tens of thousands of protocols in this thing. Some of them use entanglement swapping, teleportation, so many great features. But I'll just give you this simple scenario. So this technology is ready. It is the most advanced quantum application ever. Why? Because it's just plug and play. We already have the device in the market. You can just take the device and use it right away. They are already in use. This technology has been tested in several scenarios, in the ground, on the space, underwater, everywhere, and it's working great, and it's the future. And just to let you know, like the first bank transaction have been made using quantum key distribution have been done like 20 years ago, something. So yes, this is for the quantum networks and quantum key distribution. Next, we have the post-quantum solutions, and Yaser will go.
So we have quantum computers, or we will have more advanced quantum computers in the future. And we have quantum communication and quantum network and quantum internet. So we should protect our data which are transferred in this network or any other kind of network what can be broken by quantum machine and quantum attacker for access to quantum machine. As I already mentioned, the public key cryptography used today is based on factoring and discrete logarithm problem, which are vulnerable to quantum computer. by using Shor and Grover algorithm. So, any kind of cryptography which is based on factoring or discrete logarithm can be broken using Shor algorithm. And any kind of cryptography, as you see, SHA-2, SHA-3, AES, which are symmetric or using hash function, can be broken using, can be weakened using Grover algorithm. So we need some new solution which are not based on factoring and discrete logarithm. Is it possible to have some other problem which are still hard in quantum computer? Yes, the multiple solutions has been proposed to be immune against quantum attacker. Those solutions are categorized as post-quantum solutions, which are not based on factoring or discrete logarithm and are based on other solutions which are still immune in quantum against quantum attacker. These solutions can be categorized into 4 categories or even more, but in general 4 categories: lattice-based, code-based, hash-based, isogeny-based. The first one, lattice-based solution, is a generic term for construction of cryptographic primitive that involve lattice, either in the construction itself or in the security proof. The second one, code-based, are solutions whose security rely on the hardness of decoding in a linear error correcting code, possibly chosen with some particular structure or in a specific family, for instance, quasi-cyclic code or Gopal code. The third one, hash-based, is a generic term for construction of cryptographic primitive based on the security of hash functions. The last one, isogeny-based, which is more complicated solutions and has less computation overhead compared to other, use map between elliptic curves to build public key crypto system. It's analogous to Diffie-Hellman key exchange, but it is based on work in supersingular isogeny graph. So we have a set of solutions for post-quantum cryptography. We should now we take a look at them and review them. As I mentioned, these solutions are in 4 categories: lattice-based, code-based, hash-based, isogeny-based. Each of them is based on an underlying 1 or 2 or even 3 underlying problems. For example, it can be based on modular learning this error, short integer solution, or shortest vector problem, or fast Fourier sampling for lattice-based, or for code-based, for example, quasi-cyclic code decoding problem, or for hash-based pre-image resistance of hash function. So now let's take a look at the standardization process related to post-quantum cryptography. It starts from 2016. The first round of candidates has been submitted in April 2018 to be standardized by NIST, National Institute of Standardization. It includes 69 schemes which can be categorized into 2 categories. The first category are related to digital signature, and the second category is related to encryption or encapsulation mechanisms. The first category includes 1/3 of candidate, and the second category includes 2/3 candidate. It reduced to 26 schemes for the second round in August 2019. Again, this 26 scheme reduced to 15 candidates in 2020. These candidates are categorized to final list and alternative one. Final list is decided to be a standard, while alternative one are considered as alternative option to be standardized. The third round submissions has been reduced to eight candidates in July 2022, just recently in the last months, which include 3 signature and 1 chem in final list and 4 chem in alternative one. The blue one includes signature scheme, and red one includes key encapsulation mechanism. And you can see the list of them here. We will describe them more in the next slide. In the next slides. So we have a set of candidates. Which one is better for us? Which one we should select? So we should have a kind of evaluation criteria for that. For evaluation criteria, the most important item is security. By NIST, security is defined into 5 levels. The first, third, and fifth one are considered the hardness of the solution to break against exhaustive key search. Exhaustive key search is a form of brute force attack where the key used for the encryption of message is found by decrypting the message that have been encrypted this way, every possible key that could have been used. The second and fourth one is related to collusion search, which is related to collusion of hash function and trying to find 2 inputs producing the same hash value. Is the security only evaluation criteria we should care about? No. We should care about performance as well. For performance, we should check the size of plaintext, the size of ciphertext, the size of key, the number of bit transfer. I mean, we should evaluate both computation and communication overhead of the possible schemes. Also, it can be evaluated on different platforms, high-end, low-end, or software or hardware. Maybe on different platform has different. Each scheme has different performance. Also, it evaluates for different use cases. Maybe for one use case, we only need to encrypt one time, while we need to decrypt multiple times, or we need to sign one time or verify multiple times. So the cost of signature in this case is not important for us, while the cost of verification is much more important. There are some other properties like drop-in replacement. Drop-in replacement means that we just take, for example, RSA and put one option from here instead. And we have perfect forward security, resistance to side channel attacks, simplicity and flexibility, misuse resistance, and any factor which could hinder adaptation. So, as I mentioned, previously, we had 69 candidates in the first round, 26 candidates on the second round, reduced to 15 candidates in the third round, reduced to again to 8 candidates in the fourth round. As you see, it is categorized into 5 categories: lattice-based, code-based, multivariate, hash or symmetric, and isogeny. But as I mentioned earlier, we had lattice-based, code-based, hash, and isogeny, and I didn't discuss about multivariate because this type of scheme, there is no candidate for this type of scheme in the fourth round, which is the final round of presented by NIST recently, and it was in the first, second, and third round submitted earlier. Hence, I didn't present it as one possible option for post-quantum candidates. And each of these candidates in the fourth round has some underlying problem. Some of them is based on one problem, for example, modular varying this error, and some of them, like Liboqs, is based on modular varying this error and short integer solution. So there are 2 underlying problems, and the hardness of breaking this algorithm are based on 2 underlying problems. So these algorithms are categorized to finalist, alternative. Each finalist can be either encryption or signature, and alternative can be encryption or signature. Also, this candidate can be either lattice-based, code-based, hash-based, or isogeny. Here is a security. So this candidate has multiple implementation related to each security level. And the authors of this solution, the inventor of this solution, has been presented multiple implementation which are mentioned here. For example, for byte, we have byte level 1 and byte level 3, which are related to level 1 security and level 3 security. So here is a comparison of all implementation of all possible candidates for the fourth round of NIST for key encapsulation or encryption mechanism. Also, again, here is another list for signature schemes. So we compare security. We discuss about evaluation criteria, which includes security. Now, the next thing that we should consider is, are they totally secure? Is there any attack which may cause problem on this solution? We can claim that a scheme is totally secure. So always there's a chance that there's an attack invented to break a cryptographic solution. In general, cryptology can be categorized into 2 categories: cryptography and cryptanalysis. Cryptography, as I mentioned, include asymmetric cryptography and symmetric cryptography. Cryptanalysis can be done either on implementation or on mathematical analysis of the scheme. The implementation attack can be either active attack or passive attack. Passive attack usually contain side channel attack, or it's another name for side channel attack. Let's take a look at this attack and see which one of these attacks can cause any harm or damage to our system when we use NIST 4-round candidate. In classic cryptanalysis, we mathematically analyze crypto system. In fault attacks are semi-invasive method to intentionally induce fault to reveal cryptographic internal state. We impulse fault into the system to deduce any cryptographical internal state. In timing attacks exploit variable runtime of an algorithm. Template attack provide a sensitive device to gain access to the secret. In power analysis attacks are sample differential correlation power analysis and non-invasively, which exploit variation in the power consumption of a cryptographic algorithm. We measure power and differentiate different power for different scenarios on the system. For electromagnetic attack, we exploit radiation from cryptographic algorithm. So, finally, for cold boost attacks, exploit memory remanence to read data out of a computer memory after the computer has been powered off. Here is a summary of the attack has been imposed against NIST fourth round candidate. This include classic cryptanalysis, static time analysis, fault attack, simple power analysis, advanced power analysis, electromagnetic attack, template attack, and cold boot attack. Also, it shows some countermeasures have been proposed to immune against those attacks. Recently, some days ago, site which is one of the isogeny-based candidate has been cracked in 1 hour with one core of an ancient Xeon computer. But there are some possible solutions has been proposed to immune against that attack which should be considered more if it can protect the system site against this attack or not. Now let's take a look at implementation and see if they are efficient for our system for the system or not. We have for the implementation we have Liboqs library, which is a C library for prototyping and experiment with quantum resistant cryptography. Liboqs is a part of Open Quantum Safe project which aim to develop quantum safe cryptography and integrate into application to facilitate deployment and testing in real world content, in particular in real world context. As you see, it provides prototype integration of we have prototype integration of Liboqs with some network protocol like TLS, SSH, through OpenSSH and OpenSSH. Here is a comparison of the NIST fourth round candidate by using Liboqs library. As you see, for the first round, for example, Kyber has the lowest overhead. For the level 5, Kyber still have lower overhead. Why? For example, as I mentioned, some of the algorithm has low overhead for example, for encryption and decryption, while have high overhead for key generation. Since key generation is done only one time, this algorithm is still beneficial for us for the use cases which use only one-time key generation. Again, here is communication overhead comparison of CHEM. The same for signature computation overhead, and one of the best algorithms for signature is speed and dilithium for different levels. Here is communication overhead. Now, for migration, we have two categories of solution: encryption or key encapsulation mechanism and signature. For encryption, we have three functions: key generation, encryption, decryption. For signature, we have three functions: key generation, sign, and verification. If you want to compare two algorithms, we should compare all the functions related to those algorithms. For example, for encryption algorithm, we should consider comparison of key generation, encryption, and decryption. So we have for comparison, we should have fast computation, small communication, and confidence against quantum attacker. Also, there are some other performance metrics, include time-consuming primitive, latency, threshold, memory required, and external library dependency, key size, ciphertext size, and signature size. In the next section, here in the following, Mohammed presents some protocols which use this algorithm inside. Mohammed?
Thank you. So as Yaser mentioned, all the algorithms that we are going to use to secure our future and our information data, and as we all know, our data can be addressed, which is stored in the hard disk, and this type of data and use. If the data is stored in the hard disk, we can use symmetric. They are still secure. The main problem that we are suffering, which is in transit, if the data is, we are sending and receiving data, because they rely on public cryptography, and Yaser already talked about this. So we have tens of protocols that they facilitate this for us. If you open our page, you will use a protocol. If you download a file, you will use a protocol. If you send a message, you will use a protocol. If you do a remote desktop, you will use. There are tens of protocols that facilitate our life, and each one of these protocols lie in one of these layers of the network, and each one of them should be secure as well, because all of them are using public cryptography systems, and they are broken like close in the future. I'll just give you some of these protocols just to show you the importance of it. So we all use HTTP and accessing websites, and from now on, we think we are secure because we are using HTTPS. HTTPS is secure, yes, because it uses TLS, and TLS use public cryptography, which should be replaced as well. This is just one of the examples. Another protocol, which is SSH. If you are not opening a website, maybe you are accessing a machine remote desktop or doing other functionalities, that this protocol as well is providing these services for you to make it to make our life easier. Again, these protocols rely on public cryptography as well. We need to migrate to new protocols, new versions of them. And the problem with these previous protocols, you need to do some changes. Like here, we need the whole website should be changed. The browser should understand. But we can have IPsec, VPN. VPN, I don't need to change anything in the protocol. I will just underline protocol that create a secure channel, and I can exchange any information in that. Yes, it gives us flexibility, and it makes our life easier to secure our information. But again, all these protocols, all VPNs rely on public cryptography systems, which they are broken, and they need to migrate. To migrate, this is just an example about TLS. To migrate TLS, the first step is to find the algorithm. What Yaser has presented about the journey of NIST started from 2016, and just last month they told us Kyber is good, we can go for it as a standard, but still we need 2 years. 2 years until NIST will make it as a standard. Then after 2 years, we will start trying fifth standard. We need, like, to have TLS as a standard. There are tens of standards that they should be in line until we've had it as a standard. Then we need like CFRD, which is the Crypto Foreign Research Group standard as well. After it will be issued after the fifth standard. Then we need TLS standard after that. Then we need to adopt this new technology to send it to the end users, everybody to understand. So we need time to migrate, and it requires a lot of time to migrate all the protocols. So next, the hybrid approach will be presented by us.
So, as Mohammed mentioned, we have a couple of protocols in our network, and we are using them. These protocols are based on classic cryptography as a RSA or Diffie-Hellman or, for example, elliptic curve cryptography, which are all classic. So these protocols should be moved to the ones which use post-quantum cryptography, which are immune against quantum attacker. So anyway, this approach should be moved should be changed by post-quantum approach. So in one step we have classic, in one we have post-quantum. Is it possible to jump from classic to post-quantum in one shot? No, it's not possible. We need a transition period from classic to post-quantum, in which both classic and post-quantum are able to work, and each party can collaborate either it has classic or post-quantum. Hybrid approach, you combine classic one to post-quantum and post-quantum one. So why we need hybrid? And in general, in cryptography, we need to provide the three main concepts: confidentiality, integrity, availability. We also should provide privacy of user and non-repudiation. These things are provided by cryptographic algorithms and cryptographic approach using those algorithms. And we need to protect data in different states for this solution. Data has different state. One of the key to protect data is accounting for the possible state in which data may occur and what control available for that state. For data security and encryption best practices and recommendations, there are three states for data: as a data in transit, or in use, or at rest. Let's take a look at providing security for different states of data. The first one, which we will consider, is data in transit and providing secure communication. So we are worried about the use of data that is available today in future. There's an attack for crypto of user, and the attacker, with the help of new computer, will be able to decrypt data and get a plain text of data stored today and decrypt it in future. So we need to provide secure communication from now. We need to have post-quantum, for example, TLS right away. Is TLS the only interface we should care about? No, there are some other interfaces like VPN. We should care about all interfaces and update all interfaces to use post-quantum algorithm. Here are the list of some of the interfaces of the network: TLS, SSH, IPsec, MACsec, EWDM are some of them. In this slide, we present an example architecture diagram related to Amazon AWS, showing some variety of link, interface, and protocol that are used today. TLS is one of the first protocol AWS focusing on upgrading and integrating post-quantum algorithm. TLS was the first, but not the last one. The next question is secure communication is the only aspect we should care about? No. Why? Because data has different state, either in transit, at rest, or in use. So we should provide security for all states. Also, security is based on layering. So we should provide security in different layers, either in application or authentication, for example, JSON Web Token or TLS or IPsec and IPsec. So, as I mentioned, post-quantum algorithms are under review and analysis, and but will be resistance against quantum attacker. However, post-quantum has not been standardized yet. So we can't really do drop-in replacement. So as I mentioned, there's a possible way to use both classic and post-quantum algorithm together and combine them is available. It's hybrid approach. In hybrid approach, we can combine them such a way that we can get both the proven security of some algorithm like elliptic curve Diffie-Hellman as classic one, and potential quantum safe property of new post-quantum algorithm studied by NIST. So so we can combine those algorithms by using hybrid approach. Hybrid approach refers to using multiple algorithms simultaneously and combine the result with the goal of providing security, even if all but one of the component algorithm is broken. It's motivated by transition to post-quantum cryptography. So, why we need hybrid approach, and what's the advantage of hybrid approach? It guarantees security. It guarantees security before quantum. It also provides compliance to a standard, which we have, for example, FIPS, as I mentioned in my first slide. It also provides a smooth transition from classic to post-quantum cryptography, and it also can combine multiple post-quantum schemes together to achieve crypto agility. Imagine that we use Cypher in our scheme, in our system, and Cypher is broken. We should be able to agilely transit from usage of Cypher to some other protocol which is immune against those type of attacks. So hybrid approach provides the ability to use multiple post-quantum schemes together to achieve crypto agility. Here is an example of hybrid key exchange. We have in the first line of each side, we have classic elliptic curve Diffie-Hellman. The first one generate private and public key. The second one private and public key, and at the end we have SS1, which is secret shared key related to classic one. Also, we can have a second line related to shared secret key of post-quantum one. hybrid approach and using key derivation function and concatenation of those shared secret keys, we would be able to provide hybrid key exchange which support both classic and post-quantum one. For hybrid post-quantum, there are some standardization has been presented till now. The most important one is NIST post-quantum cryptographic standardization process, which is named as NIST SP 856 Rev 2. And there are some other standardization have been presented, but they are not as important as first one. So let's take a look at NIST. NIST standardization for hybridization of key exchange is based on the protocol presented before quantum time. It is used to combine a static public key and ephemeral public key, and it used to combine them and make a hybrid key of static and ephemeral key. Here is a detail of this protocol presented by NIST. As you see in this standard, they use concatenation of two secret key as a hybrid one for classic and post-quantum one. However, this concatenation of secret key of classic and post-quantum one has a problem. In any of the key derivation methods specified by NIST in SP 856C, the revision would permit a concatenation of secret key of classic and secret key of post-quantum to serve as the shared secret key instead of only classic one. What's the result? This require insertion of secret key of post-quantum in the coding of the scheme, and the FIPS 140 validation code may need to be modified because you see the size of the key is changed. It's concatenation of the two keys. So these two keys cannot be just used as a drop-in replacement. So FIPS 140 need to be changed. This means that as you are testing and experimenting in preparation for your migration to post-quantum cryptography, you can do it in a more realistic situation on an environment that use BIP certified software. So we should think about it more, and we should change more things on the system. Here is one possible solution which is presented by IETF organization as a possible solution, but anything which accept NIST standardization still should use the first one, and we should think about how we can solve this problem. In the next part, I asked Mohammed to talk about migration strategy. Mohammed, please.
Thank you, Yaser. So, as we discussed throughout this workshop, so we moved to this migration strategy, which we started by the exploration. Why the exploration? Because we need to search for new solutions, either quantum or post-quantum. And then we move to the standardization. Yeah, and we need these things to be standard because we need all of us to use the same thing. And then we have list of protocols that we need all of them to be ready for the new threat. Also the implementations itself, how to evaluate all their implementations and how to choose which one is the best for us. And we have other things, I'll go through them quickly. The first thing, which is the community. So the internet is not isolated place like I live there alone. So we are there, all of us. We communicate with each other. So either we all migrate or we all stay here. So why? Because And if we migrate, we should migrate all of us to something, to a standard that we all will use it. Why? Because let's assume you use Psi and I use Kyber, but I don't trust Psi. I will not send my confidential information using this algorithm, which will make us we cannot communicate securely because we are using different algorithms, different protocols. Your protocol is not secure, I will not communicate with you because I will send my confidential information. So community is really important because we all need to migrate, we need to collaborate, and we have several challenges in this. Who will coordinate what system, because we have different systems, how can they communicate, and how to communicate these things to the end user. So the community is a really critical step in the migration. The second thing, which is the research. Yes, we choose new algorithm, we migrate to it, but this is not the end of the story because like RSA gives us so many advantages. Like we have homomorphic encryption, we have key exchange, we have group key exchange. Do these algorithms provide this? Not yet. So we need to do research to make them ready to give us the other applications that we also need. So the last thing in the migration, which is agility, crypto agility, which is the most important step, as Yaser mentioned before. Why? Because let's assume we move to a new algorithm, and maybe this new algorithm just get broken. So what can we do? We go back to RSA, which is broken as well. So what are the options that we have? So we made a mistake. Some companies and organizations, they already made a mistake by being hard-coded to factorization problem, which is RSA algorithms. Their machines, devices, they have even hardware that they only speak RSA. You cannot replace these devices. There is some expectations like maybe there are a huge percentage of companies they cannot migrate. Why? Because they need a big investment to buy new devices, new systems, because they need to change the algorithm just. Can you imagine? So what we need to do, because we should learn from the past, if we move to a new algorithm, new standards, we should move systematically and we should be flexible. Any change, like after a year or two or something, new threat comes, this algorithm, these things should be changed quickly, and it doesn't have to cost us a lot of time and money, because just recently, site get broken. Just imagine, just last week. So crypto agility is a must. By having crypto agility, it will give us ability to respond to an incident so quick, and it will give us ability to know what we have, what do we have, keys, certificates, and all these things. And it will allow us to automate all these things, to automate all this process, and the switches. We have to automate these things because we have a lot of devices, a lot of things that we need. So we will end up by we should have some tools that automate these things for us, especially for big organizations. So we reached the conclusion of our workshop today, and we hope that you learned a lot. And we try here in the conclusion to summarize a list of recommendations and final remarks for you. So what we start here by what each organization or company should need to know. They need to know first several things. The first thing they need to know, there is threat, because there are some companies and things they don't realize the threat yet, but there is threat. This is the first step. The second step is they need to know what they have. Yes, in your organization, maybe you don't know you are using RSA. Why? Because you open the website, you don't even know that this website is using TLS. TLS is using DVM and these things. So you don't know. So what we need now to know is we should know all these things that have been used in our organization. What algorithms we use, what digital signature schemes, what identity authentication processes, authorization, everything in your organization that use public cryptography, it should be known by now, at least. And we need to know the scope of the effort, the scope of the migration. Yes, we will migrate. How big the company is, what are the devices that need to be replaced, what the systems, and so many things that we need to know them. And the sad story is many organizations, they don't even know where is this cryptography is used in their organization. So we need to know all these things. And once we decide to migrate or we choose algorithm, again, there are so many things that we should know it first before choosing anything. Yes, let's say Kyber, we will move to Kyber. But who developed Kyber? Maybe a naive programmer was there, he put like some mistakes in the code itself. The implementation should be secure. Not only the algorithm, the implementation should be secure against any side channel attacks. And which is what all these algorithms now suffer. Even side, it gets broken because of side channel attack as well. So we need to do the implementation verification tools. We need to know the operation system dependent. We need to know devices, the protocols, everything in the organization. We need to know them beforehand. So what we need to do as well, we need to do to identify our sensitive information. Maybe you have information that's not sensitive, so don't worry about it. But we need to identify and classify our information based on their sensitivity level. Let's call it sensitivity level. And the shelf lifetime, as Yaser mentioned in the risk assessment. How long do you need this information to be secure? 5 years, 10 years, maybe 100. We need to know all these things, and we need to know our limits. The key sizes, the network overhead, and also the latency. We should know the limit as well, because big companies, they don't care. Small companies, maybe they care because they might need to change the infrastructure of the network. So there are several things that we need to know them. Also, we need to know who are the suppliers, the owners of these devices, and all other things. As a final remark, because I think we exceeded the time, there's not much time for questions. So as a final remark, we all know migration is inevitable. We all will migrate to new algorithms, new systems. And migration starts from now. Why? Because we need time. We need time to have standardized algorithm, protocols. We need time to identify the scope. We need time to do the risk assessment. We need time to do the cost analysis. We need time to do so many things. We need time to all of us move. We will wait for the weakest point even to move with us. Not only the giant companies will move, but the smaller ones as well, their clients, everybody, we need to move. And what we think as the hybrid approach are plausible, are good, because they give us the ability to go forward and backward. And also the last and the most important thing, crypto agility is a must. In each migration, the new migration or the new plan should adopt agility level on. So I think this is the end, and we are happy to answer any questions.
We have almost 20 minutes. If you have any question, 18 minutes. If you have any question, we would be happy to answer you. Please.
Okay, so 2 questions here. By the way, congratulations for the great talk. I found it very insightful, and a lot of things to learn, a lot of interesting things to look at. And the first one was about the first part of the presentation. We were talking about some algorithms, right, and some problems that are solving. So, for example, the Gruber's algorithm that deals with this unstructured environment and a search problem with which we have so many things to consider, because that's a just a paramount problem in computer science in general, and rightfully so. But then my question will be, regarding the adoption of these algorithms, where can we adopt them other than cryptography in the cybersecurity practice? Because, for example, when we think about IoT, for example, we have thousands of devices out there, and there are many other problems to solve regarding the search problems and the optimization. So that's the first one. And the second one would be regarding the adoption and the horizon from now on, right? So we're talking about the adoption of these mechanisms and then the improvement of our systems. But then, in your opinion, what would be the scenario that we'll be having like in 10 years from now, and what would be the ideal scenario that we'd have?
So we have, if I can answer this question, we have three things that we can consider. So actually we have quantum algorithms, which is like Grover and Shor. This, we don't worry about them. We will not install them in our machines and in IoT devices. Only the attackers will use them. So even a giant computer will solve the problem. We will just have it quantum as a service. You will send the information, it breaks it for you, and it gives it back, because they are really big devices. So this thing, we will not worry about their implementation and how we give them to the end user, because quantum machines will not be for the end users. They are just for big calculations and this thing, like supercomputers. This is the first thing. The second, we have 2 types of solutions. We have the quantum solutions, which is quantum key distribution and these things, and we have the post-quantum algorithms that Yaser listed. For the quantum key distributions, we have small devices that we plug in our servers, and they work like they communicate to each other, and we don't think, maybe there are some works that try to make even IoT devices that can use QPD, but it's not that big devices because they are just send light and receive light, but they need high quality devices. They will increase the cost for sure. This is one thing. The last thing, which is algorithms, that classic algorithms like Kyber. Kyber is just simple algorithms that do mathematical calculations. Which is the post-quantum solution. Yeah, the post-quantum solution, it's comparable, like if we compare it to RSA algorithm, the one that we are using, it's sometimes faster, it has less key, it has less overhead. Maybe this solution is even better than the traditional one. So there is no big problem in installing this algorithm because they are really good, like in terms of communication, key sizes, and computation as well. I hope I answered the question.
I want to add one point that still the new algorithm has more overhead compared to RSA and electrical cryptography, which is commonly used with it. But with the progress of computer, we will be able to use them, but we should have a plan to use them in the future.
Yeah, just want to come here. I think it's very commendable to see you guys working on that, because I think it's an important problem, and then that's something they're going to be facing in the next few years, right? That's not far away for now, so that's really nice. And then the other challenge that you mentioned, Mohammed, by the end of the presentation, you or Yaser as well at some points, I think is the awareness, right?
Yeah.
The acceptance. That's something that we're going to have.
Accept the threat, and we should work.
Yeah, that's
act now. Yeah.
Right. So that's something very interesting that you guys are covering there, and then just congratulations for a great talk.
Thank you. Any other question? Maybe any people from online? Yeah.
So,
any question here or online?
Yeah, I have a question. In general, in a qubit, we can store either 0 and 1. Okay. In general, in a qubit,
yes.
We can store either 0 and 1, right?
Or both.
Yeah.
And
So
we can store 0 or 1 and
is
both.
there any possible way we can store 3 bits and 4 bits in a qubit?
In a single qubit?
Yeah.
So,
A good question.
it's a tricky question because actually how it works. Let me just, maybe I can use this. So I mean, if I can just make it simple how it works, because we are in the quantum world, we are dealing with wave functions, and just if I talk classically now, like in the classical world, we can have this wave, and we can have this wave that's faster. If you just sum them up using Fourier transform, you will end up with this wave. This wave is just the summation of these two. So classically, and this is how the communication works. Like we send like signal that could be several signals. I combine 10 waves in one wave, then I send just one wave, and then the other end you use Fourier transform like reverse, and you will like open it to its ingredients. You will get the 10 waves as well. This is what's happening actually in the quantum world, which is we have the 0, we have the 1, we deal with them as waves, we combine them into one wave, we deal with it, which is the combination, then we can extract its ingredients. I like the question. My imagination is it could be, but I don't know. But theoretically, yeah, but physically, I don't know how.
I want to add that one point, and it's that by the progress of technology and inventing more fault-tolerant qubit, maybe we would be able to transfer more data, even using some maybe parallelization.
If I use the electron, I cannot store more than that. I mean, if I use the electron representation of the physical device, I don't, as far as I know, for the best of my knowledge, the only thing that I can show is 0 or 1 or both. More than that, maybe a bigger nucleus that have more electrons, which is more qubits.
Great.
Thank you.
Maybe you should think more about
I
that.
should read about it.
So, any question? Any more question? Yes, please.
So I guess just in general, how early do you see the adoption of quantum computing becoming something that's like commercially available and where you're gonna have like those big security problems for like just like a general user rather than like a company that adopts a quantum computing approach?
For general user, it's tricky. Like it's there are some expectations. It will never like reach like now you have phone or laptop like for normal users because it requires like some of the implementations, the one that use superconductor, they require a really an absolute zero temperature. We cannot accommodate this, but there are some other implementations that they use photonic quantum computers. They work in the normal room temperature, but anything can affect them. Like, yes, they don't need lower temperature, but any noise, anything around it, it might affect its calculation. So, and I don't know for sure, but like the expectation is they will be only used like as a service, not for everyday usage. Because what we have currently, they are good. They give us the services. Only when we have a big problem, we give it to the big guy to solve. So that.
Also, I have a question, maybe a very simple question.
Yeah.
As we know, blockchain is a very promising technology and has solutions for many problems.
Exactly.
I was wondering, in the quantum world, which changes the blockchain needs? Just the hashing algorithm, or there is other kind of changes to be still effective in that world?
So we have two attacks for the blockchain that a quantum computer can affect it. The first one, which is the hash function, Grover algorithm divided by half. This is the first attack. Like the hash function itself, it's weakened using quantum computer. The second thing, which is now to be a member of blockchain for the mining, what's the problem that currently have? Our machines are not efficient enough. Just imagine if you have a machine that's equal to like 30% of the network. Like now, if you have 51% of the computation power of Bitcoin, you control Bitcoin. You have the computation power. But imagine you have a quantum computer that can give you this advantage of having the computation power. You will not break the hash function, but you will control the network because you have the computation power. So there are two sides. Either you gain the computation power by having such powerful machine, or you break the hash function, but breaking it is not possible. It's just weakening it.
Jane, I want to add one comment. There's a comprehensive study of using post-quantum cryptography and usage of that in blockchain. I can send that paper to you. I think it's around 20 pages. And it comprehensively evaluates how we can use post-quantum cryptography for blockchain. And that one is the only paper I have seen about this subject.
Good question. It's not easy. Thank you. Do we have any online questions?
So, any question online? No question?
No questions here. So, thank you.
Thank you, everyone, for taking part.